Welcome back. So the last time we were reviewing open subsets of Rn, and we defined the notions of interior points, exterior points and boundary points. An open subset is one where all the points are interior points, right? So we need to be a bit careful about these definitions. So for example, if you take 0 1 cross, let's say 1 comma 2, and say 0 1 but the open interval cross 1 comma 2, suppose this is S1 and this is S2, right. Now what is the boundary of S1? Boundary points are points that are neither interior nor exterior, right. So morally the boundary point of S1 and S2 they will coincide and they will both be the rectangle, namely you take 0 cross 1 2 union 1 cross 1 2 union 0 1 cross 1 union 0 1 cross 2. Okay, so both the boundaries are these. Why? Because if you take any point on this boundary, if you take a small ball around it, no matter how small a ball it is, it will contain points from within the set as well as from outside the set. And these are the only points for which this happens. If you take any point here, it will be interior. If you take any point here, it will be exterior, right? So the same set can be the boundary of two different sets. Okay, so this is an important little point. Okay, so here's one more definition, the third definition if you wish. What's a closed set? A closed set is one whose complement is open. Okay. So for example, if you take 0 1 cross 0 2, this is closed. And why is this closed? Well, what is the complement? I mean, from the picture it's clear the complement, if you take any point in the complement, you can always find a small enough ball that does not intersect this rectangle. But again, I urge you to prove this rigorously. Why is this closed? In other words, why is the complement of this open? But these definitions are very subtle, right? Closed and open sets are not like doors. It's not like every set is either one or the other, right? So for example, a set, okay, maybe this remark or caution if you wish, a set can be neither open nor closed. Right, for example, if you just take an R, if you take a semi-open interval, this is neither open. Why is it not open? 0 is not an interior point. It's not closed either because what's its complement? The complement consists of this. And the complement is not open because 1 is not an interior point, right? That's one thing, one remark. Another remark is that a set can be both. Okay, what's an example of such a thing? All of R itself. In R is a subset of R, or R2 is a subset of R2, and it is certainly open, obviously. I mean, if you take any point and any ball around it will lie within all of R2. It is closed also. Why? Because its complement is the empty set. An empty set is trivially closed, right? Why not? Why is it closed? Because if I take the complement of the empty set, it's open, right? By the way, the empty set is both open and closed. Likewise, for example, if I take the empty set, it's also open. Why is it open? What does open mean? If you take any point in the set and a small enough ball around it must lie within the set. If the set doesn't contain any points at all, it's vacuously open, right? It's open for trivial reasons because you don't have anything to test. Yeah. one can prove, again this is an exercise, one can prove that, again this is an exercise. By the way, homework will contain some version of these exercises, but whether it will or it will not, the best way to learn the subject is by pausing the video and trying to do these exercises on your own right now. Yeah. Okay, so one can prove that a set S in Rn is closed if and only if it contains the interior points as well as the boundary points. Yeah. So that's that's the definition of a set. And for example, if you take 0, 0, just the point 0, 0, this is a closed set. Okay, why is it? I mean, this theorem doesn't contradict this point. The interior of this set is empty. The boundary of this set is S itself, right? Okay, right. This point is not in the interior, it's not in the exterior either, because it's already in this set. So exterior points contain points outside of S, right? All right. Okay, so here are a couple of other definitions that we need to recall, and then we will move on to the actual heart of the subject. We'll actually start the course in earnest. All of this is review, so to say. So path connected sets. A subset S of Rn is said to be path connected if, as the name suggests, there is a continuous path from a point within the set to another point within the set that lies entirely within the set. That is, you don't have to go outside the set, right? So how do you make it rigorous? If for any 2 points, every pair of points A in S and B in S, so I will put the vector sign most of the times, but if I don't put the vector symbol, it's understood. Okay, it's understood from the context. Yeah, there exists a continuous function gamma from 0, 1 to S in Rn. What does a continuous vector valued function from 0, 1 to S mean? It means that each component is continuous. Each of these is a continuous one variable function. We know what it means to be continuous in one variable. We have not defined what it means to be continuous in more than one variable, right? So if I have a continuous function such that gamma of 0 is A and gamma of 1 is B. That's exactly what a path joining 2 points is, right? Simply a continuous function, and this entire path must lie within S. So the image of the path must be within S, right? For instance, this ball is connected, path connected, sorry. Why is it path connected? If you take any 2 points within the ball, right, if you take a straight line joining them, that straight line will lie entirely within the ball. Again, I urge you to prove this rigorously. Okay, write the equation of the straight line joining the 2 points and prove that it indeed every point on the straight line does lie within the ball. Okay, right. So a path connected set, a path connected open set is sometimes called a domain. Why is it called a domain? Because it's a good candidate for the for the domain of a definition, for the domain of a differentiable function, for example. That's why it's called a domain. So when I say a domain, I typically mean a path connected open set. Now, here is one more definition which is very close to path connected in a way, but it's not obvious that these two definitions are close to each other. When you think of a connected set, what you would have in mind is, what's a disconnected set, right? So a disconnected set is two blobs, if you will, right, that have nothing to do with each other, right? So how does one make this intuition of ours precise? So a disconnected set S in Rn is a union of two sets A and B, and A intersect B is empty, right? This is A and this is B, they are two blobs, and A is the intersection with an open set, open in Rn. B is the intersection of S with another open set. In other words, so suppose I take, let's say in R2 I take this line, okay, or if I take two lines for instance, and the set is the union of the two lines, this is disconnected. Why? It's a union of A and B which don't intersect each other, right? And if I take two small open balls, I take an open set in Rn and intersect it with S, this is U intersect S is A, this is V intersect S is B, right? So that's why this is disconnected. In other words, a disconnected set is something that cannot be written as a union, as a disjoint union of two open subsets of S. By that I mean two subsets of S which are disjoint, and each subset is the intersection of some open set in Rn with S. Okay. Turns out, so a connected set is something that's not disconnected, right? So connected set is something that cannot be written as a union of two disjoint sets, each of which is the intersection of an open set in Rn with the set. Turns out every connected open set is path connected and open, and the other way around. So if you are connected and open, then you're path connected and open. If you're path connected and open, then you're connected and open, right? Yeah. But not every connected set is path connected. This is not true. It certainly is the case for open sets, but not in general. Okay. So lastly, compact sets. So these are sometimes called sequentially compact. Okay. A subset K in Rm is called sequentially compact, or simply, it's also simply called compact, although that word is used for something else, but these two coincide in the case of Rn. Okay. So I'll just say sometimes compact subset of Rn. What I really mean is sequentially compact. If every sequence has a convergent subsequence. What's a subsequence? It's a sequence in its own right, but it's a subset of the original sequence, right? In R, sequentially compact is the same as being closed and bounded interval, closed and bounded. In fact, in general, right, in Rn, sequentially compact is equivalent to being closed and bounded. That means if you take a set S, subset S of Rn, it's sequentially compact if and only if it's firstly closed, secondly it's bounded. Bounded simply means that the subset is contained in some large ball. There is some ball containing it. The word large is not precise. There's contained in some ball of finite radius. Okay. Now, this needs proof, of course, but we won't bother with the proof. For n equals 1, for R, this has a name that you know. It's called the Heine-Borel theorem, or depending on how you want to call it, the Bolzano-Weierstrass theorem. Using the n equals 1 case, you can prove the n larger than 1 case as well. You can use this to prove this. Okay. Well, I leave this as an exercise if you want to prove it, but you can also take it on faith if you've not seen this fact earlier. In fact, I would suggest you do it as an exercise, don't take it on faith. The idea is simply this: if you take a closed bounded subset of Rn, if you take a sequence and if you take each component of the sequence, you get a bunch of real numbers and they are closed and bounded, so they will have a convergent subsequence in R because of the n equals 1 case, and that's how you can produce a sequence. But why don't you do it rigorously? Yeah. Okay. So this finishes our review of linear algebra and the basics of topology in Rn. So now we begin the course in earnest. We actually start multivariable differential calculus, and towards the end we will also do some ordinary differential equations. Yeah. Okay. So the first thing one does when one talks about calculus is limits and continuity of multivariable functions. Okay. Okay, so suppose S is a subset of Rn and F. I will not always put this vector valued symbol, okay, on top of a function. It could be vector valued even if I don't put the vector sign, but for the first few times I will put the vector symbol just so that we are all on the same page. So let A be in Rn and B in Rn. Okay. We want to define, before giving the definition, let me give some motivation, and we want to define limit as x goes to A of f of x. We want to say that this is B. So how can we make this definition? We would want to say that f of x gets closer and closer to B when x gets closer and closer to A. More precisely, you can make f of x as close to B as you want if x is sufficiently close to A. There is a slight subtlety in this whole story though, and this subtle point even occurs in one variable calculus, although you may not have seen it. So for example, suppose what happens if A is not in the domain of the function? So for example, in one variable calculus, suppose I define a function of one variable as, let's say it's 1 when x is larger than or equal to 1, x is larger than 1. Let's say it's x when x is less than 1. Can we even define this limit? Yes, we can, and the answer is indeed 1. So in other words, 1, that is x equals 1, is not even in the domain. In other words, this function, this point is not even in the domain, and yet we can make the definition. So it's not important for A to be in the domain. A need not B in S. This raises a very subtle problem though, that you may not have seen in your one variable calculus course, but even in one variable calculus. Suppose S is simply the point x equals 0 in R, okay, and f of x is, let's say, x square. Does it even make sense to talk about this, right? I mean, what we would like to say that x gets closer and closer to 0 and f of x gets closer and closer to something, but the trouble is there is nothing close to 0 other than itself. Or for example, let's say take x goes to 1 f of x, right? This 1 is not in the domain, but there's a deeper problem than merely not being in the domain. Nothing close to 1, nothing close to 1 is in the domain. Here, despite 1 not being in the domain, it was still okay because there were points arbitrarily close to 1 that were in the domain, right? So to make this definition, we will require our set to be of a very specific type, not our set more than our set, the point itself. If A is a limit point of S, that is, there exists a sequence xn vector in S such that it converges to A, then we define this limit as x goes to A, f of x equals B as follows. For every epsilon greater than 0, there exists a delta greater than 0 which depends on epsilon such that whenever x is very close to A but it need not be exactly equal to A, f of x is epsilon close to B. Okay? So for this to make sense, there must be points which are at least some distance away from A in the set, that is, this must happen. If this doesn't happen, if A is not a limit point is called an isolated point. Isolated point. But belonging to S is called an isolated point of S. Okay? So for isolated points, the notion of a limit is it's problematic, right? It's not a good definition rather. Okay? Right. But in any case, wherever we'll end up using the definition, our set, the thing we are taking a limit to will be a limit point of our set. Okay? So in practice, we don't have to worry about the subtlety, but for making a definition, we obviously have to be careful. So informally, limit as x goes to 0, f of x minus b is 0 in the one variable sense. But this is not really a rigorous mathematical concept because this f of x is not really a function of this, right? So this is only in the informal sense. Okay? Well, this definition is equivalent to demanding that limit as h goes to 0, f of a plus h is s. Sometimes it's convenient to say this, right? Okay. So here's another definition. A function f from S in Rn to Rm is said to be continuous at a point A in S if either A is an isolated point of S, or if it's if it is in S but it's a limit point of S, then this is the case. It can potentially be outside of S and not be a limit point. So it's neither an isolated point nor a limit point. In that case, obviously it doesn't make sense to talk about continuity, right? Again, this is a technicality. If you're not happy with the technicality, just, I mean, you have to be aware of it, of course, but for moving forward, pay more attention to this, okay? Right. Okay, so here is a proposition. It's an easy enough proposition to state and prove. Limit as x approaches a, f of x equals b, if and only if each of these limits for each of these components exist and they are equal to this component, okay. And why would that be? So it's a very simple thing, but we will prove it nonetheless so that we gain practice on how to do this. Suppose this limit exists. I want to show that each of these components, their limits exist and they are equal to what we would expect. Well, what would it mean for this limit to be equal to this? So given epsilon positive, the fact that this limit exists implies that there exists a delta positive such that, so this is one direction, whenever 0 is less than x minus a is less than epsilon, f of x is epsilon close to b, okay. Now what is this? This is certainly larger than mod fi of x minus mod bi for all I. Why? Because this is equal to square root of these things squared. So of course you can drop the others and get an inequality, right? So in other words, given epsilon greater than 0, there exists a delta so that whenever this happens, this is less than epsilon, right? Because this is less than this and this is less than epsilon. So by definition, this is true. What about the other way, right? So given epsilon greater than 0, potentially for each component there could exist a different delta such that whenever x is close to a, but the closeness might depend on I, fi of x minus bi is less than epsilon, right? Right. So rather than saying epsilon, maybe I'll say epsilon, I'll make sure this is less than epsilon divided by n. Why? Because I can, right? I mean, no matter how small an epsilon I choose, I can always do this. Right. Okay. Now what we can do is choose delta to be the minimum of all these delta epsilon i's, right? So whenever this is less than delta epsilon, which is less than delta epsilon I, this happens, right? What does this mean? What is fx minus b? This is square root of f1 of x minus b1 square plus so on. This is less than square root of epsilon square by n square plus epsilon square by n square, which is epsilon divided by square root of n, right, which is less than epsilon. So both directions work, okay. All right. So this is a simple enough proposition, but just for our own practice, I have proven it in detail, yeah. Okay, so here is a theorem which is very useful, and this is similar to your one variable calculus. If f of x is less than g of x, if one of them is controlled by the other, and as x goes to a, the limit of g of x exists and equals 0, then the limit of f of x also exists and equals 0. Okay, so this is actually larger than 0. So if f is sandwiched between two things, and if this goes to 0, this is already larger than 0, so this will also go to 0. Okay. In fact, we can generalize this. Suppose f of x is sandwiched between two things, g2 and g1, and as x goes to a, if this goes to 0 and this goes to 0, so will this. This is the theorem. Okay. Now, why is this true? How would one prove such a thing? Well, this is an exercise. It's not at all hard. Well, what would the proof entail? We want to show that this can be made less than epsilon if x is close to a, right? Now, of course, this can be made less than epsilon if x is close to a, right? So, obviously, so this can be also made less than epsilon when x is close to a. This is actually a red herring. Okay, this is not even needed. Okay. This follows from this, right? I just stated it just to make the sandwich look nicer, so to say. But yeah, right. Okay, thank you for joining. We'll continue the next time.